Hello everyone, my name is Mansaba Gohil and today I will be presenting and reviewing the research paper titled Dynamic Role Discovery and Assignment in Multi-Agent Task Decomposition. And this paper was published in Complex and Intelligent Systems in the year 2023. This paper focuses on improving multi-agent reinforcement learning by enabling the agents to dynamically discover and switch roles during cooperative tasks. So today's agenda is that I will briefly talk about the focus and the problem that is covered in this research paper. I will talk about the computational methodology and its dataset and the experimental results. And finally, I would give my remarks and the critics or any suggestions that I have. So, in multi-agent systems, complex tasks such as robotic coordination, swarm control, and distributed planning requiring breaking a large task into smaller subtasks. Traditionally, engineers usually and manually define the roles. For example, agents may be a leader, a resource manager, a follower, also known as attacker or defender. However, manual role definition has three major limitations. It requires domain expertise, it does not scale well, and it cannot adapt when the environment changes. So, at the same time, multi-agent reinforcement learning faces a fundamental challenge. As the number of agents increases, the joint action space grows exponentially. This makes the exploration inefficient and training unstable. So, existing approaches fall into three main categories. What are these categories? The centralized learning, which has scalable issues and requires global information. The second category is the independent learning. It faces the issue of instability because the agents ignore the coordination. And the third category is centralized training with decentralized execution, also known as CTDE, which is better but still complex in the large action spaces. So we move on to the role-based systems, which exist, but they also have some limitations. In role-based systems, they require predefined roles, depend on prior knowledge, and cannot adapt dynamically. On the other hand, we have role-free systems. Role-free systems require massive exploration and waste samples, which is a drawback, and it performs poorly when it comes to difficult environments. So, in this paper, they propose a dynamic role discovery and assignment, which is also known as the DRDA. Instead of manually defining the roles are learned automatically from the interaction of the data, and based on the data learning, the multi-agents get choose the role on their own. So the key idea here is to discover roles from action representation, restrict each agent's action space, and dynamically assign roles during the training. This shifts the role assignment from manual engineering to data-driven learning. This environment is modeled as decentralized partially observed Markov decision process, or DAC-POM-DP. This means that each agent observes only partial information. Agents select action space independently. The agents select actions independently, and all agents share a global reward. The training paradigm is centralized training with decentralized execution, the CTDE. During training, a centralized critic has access to the global information. This improves the coordination learning, and during execution, each agent acts independently using only local information. The framework builds on QMIX, a value decomposition method that factorizes joint Q values while maintaining a monatomic constraint. This framework has three main components. First is the role discovery. Now, what's a role discovery? A two-layered action encoder that converts one hot actions into vector representations. Action contributions are calculated using the Q values. This measures how each action contributes to team reward. K means clustering groups the K means clustering method groups the similar actions into roles. The number of clusters are in this paper that when the value of k is 3, it is taken for homogeneous enemy settings, and when the value of k is 5, it's taken as heterogeneous enemy settings. To ensure that the roles are distinct, the authors introduced the L2 regularization to maximize the distance between role embeddings and a combined loss function, including the prediction error and the role separation. This creates a meaningful latent role representation. Well, we move on to the second step, the second category, which is role selection. Each agent must decide which role to take. A GRU encodes a trajectory history. A consigned similarity is used to match the agent history with role embeddings. And a straight-through Rumble softmax is used for differentiator role sampling. A Q-mix mixing network estimates the global Q value for all of the assignments and the agents. Two regularizations are used in this category, and they are introduced. Long-term versus short-term reward regularization, which means that some roles focus on immediate reward, and others focus on the delayed reward. There's also a second regularization, the KL divergence smoothing, which means that this basically prevents agents from switching roles too frequently, which stabilizes the training. And the last category, the last portion is the role policy learning. Once a role is selected, the agent uses a role-specific Q network. The action space is restricted to the role's subset, and agents playing the same role share the learning. This reduces the exploration complexity and improves the coordination. The overall objective is to maximize the expected discounted cumulative reward across all of the agents. Now, the pipeline, as I've explained, focuses on the actions. It goes through the encoder, which uses the K clustering method. Once the roles are defined, the agents go through the role selection process. And the last category is the role restricted policy. And after that, the queue mix takes place to select the queue value of all of the agents. That's the basic pipeline that's shown in the slide. As you can see, I've explained the pipeline. Now moving on to the results. The experiments were conducted using this SMAC benchmark, which stands for StarCraft Multi-Agent Challenge. The SMAC is a cooperative multi-agent benchmark built on StarCraft 2, where agents must coordinate to defeat the enemy units. Now, as we saw as we saw in the previous slide, there were datasets and data source using the SMAC benchmark and the maps. Now, you may think that what are the easy, hard, and super hard maps? This refer to increasing level of the task difficulty. Easy maps, straightforward and compact scenarios. The hard maps require better positions and coordination, and super hard maps refers to requiring precise strategy, exploration, and coordination. For example, corridor map, which is a super hard map, agents must form a wall formation, which is a narrow passage to survive the waves of the enemies. It requires a precise coordination and positioning. The second example is the 27M versus 30M. The 27 Marines must defeat the 30 enemy Marines. A numerical disadvantages scenario requiring strategic positioning. Now, so that was the main data source and the setting which is taken into this paper for the results and experiments. Now, what was the training setup? The training steps were 2 million. The RMS group optimizer was used. Replay buffer size was 50,000. Discount factor gamma was 0.99. And GPU used is RTX 2060. And the training time the paper mentioned is 12 to 48 hours. Well, let's focus on the performance results. The hard maps, on average, the 20% mean rate improvements over the baselines is shown. When it comes to super hard maps, average 55% improvement is shown, and corridor map has 70% improvement. Whereas the 27 marine versus 13 enemy marine scenario has about 40% improvement. On one hard map, convergence was about 28% faster. This shows the framework is especially effective in complex, exploration-heavy environments, which is very helpful and shows the difference that it has made for multi-agents. Now, there's also a mention of ablation study. Now, what is an ablation study? An ablation study removes specific components of the model to measure their contribution. The authors removed restricted action space, in some scenario action representation learning, and clustering mechanism. Performance, when this happened, the performance dropped by 55 to 60% on average. This demonstrates that role restriction is critical, action representation is very helpful, and proper clustering significantly impacts the performance. The results show that dynamic role discovery has improved coordination, especially in difficult tasks. Now, on the screen, I've taken the pictures from the research paper to show that how much difference both of the methods are making, which I have explained in the previous slide. Well, this research paper had definitely proven its importance and its impact. But so firstly, I would like to talk about the strength that it has covered. It has a strong performance on hard task and efficient exploration and clear architectural contribution, whereas it also has some limitations. It is limited. It has limited improvement on the easy maps, and it requires manual tuning of clustering number k. That cannot predict the k. We have to input it every single time. Evaluated only on SMAC SAMC benchmark and built only on QMix architecture, which also has some problem. And computational overhead is not deeply analyzed. So if I were the author to make improvements, I would test on additional benchmarks such as multi-agent particle environment or Google Research Football. I would take other environments. I would also compare with newer value decomposition methods like Qplex or Queton. I would introduce adaptive clustering instead of fixed K, and I would like to use and add communication modules and mechanisms. I would also provide computational cost and scalability analysis. And I would also like to test this on more real life examples and real robotic systems. I would also incorporate explainable AI techniques to interpret the learned roles. These improvements would enhance the generalization and practical scalability, which can be useful in different scenarios when we're using in real life applications. So I would like to conclude it that by saying that this paper advances multi-agent coordination by enabling dynamic role discovery through reinforcement learning. It reduces exploration complexity, improves scalability, and it definitely enhances the performance in difficult cooperative environments. The work demonstrates how role immersions can be learned rather than engineered. And I would like to conclude by saying that this paper truly studies the multi-agent dynamic approaches. It made me learn new concepts and new terms that I did not know before, and it definitely covered its impact, but it has a lot of space to grow. So that's it. And thank you for listening. If you have any questions, I welcome them now. Thank you.